here's a quick recap for what we did last time. Basically, we proved the following. When mu is a additive function on an algebra of sets A, and non-negative also, then you get this nice criterion for countable additivity, which is mu is countably additive if there is a compact approximating class K for mu. So we defined what it means for a collection of sets K to be a compact class, and we also wrote down that condition flower that I labeled flower last time, which tells us what it means for it to be an approximating class for mu, for a certain additive function mu. So roughly, compact class just means that it's a collection of sets for which all countable empty intersections are finite empty intersections. And to say a collection of sets is an approximating class for mu, well, that was that long-winded condition that we labeled flower. This was theorem 143, by the way. Now, for today's lecture, I want to look at a couple of examples, a couple of really important examples where we apply this and develop our measure theory in R and Rn a little bit. Not all the way, but just one step further than we have so far. And to get these examples working, it's actually going to take a lot of work. And working out the details is going to take us on a little bit of a sidetrack from the textbook. And then hopefully we can wrap that up today and then return to the textbook for the next section in Friday's lecture. So today is examples and filling in details for those examples. So I know it's been a while, but do you remember this set that I built up during the very first lecture about measure theory? This was sort of an example just to motivate, at the time, the problem of trying to come up with a notion of measure. This was the collection of elementary subsets of the unit interval. So that meant the collection of finite unions of more basic sets, I guess intervals. And I don't remember if I had a good notation for the finite unions, for like the more basic sets that this was built out of, the intervals. But let me just establish one now. Maybe I did not previously have a notation for it, or I had a bad notation. But now let me use mathfrak A subscript 0, so A naught. So let's just make that the collection of intervals living inside the unit interval. So all four types. Now, at the time, we didn't really have the language to describe what kind of thing we were working with, this A naught thing, but now we can say this is actually a semi-algebra. It's a semi-algebra of sets on the unit interval. And we're excited about that because we now have a theory, where back then we didn't really have a theory to apply, right? We just sort of were trying to do everything explicitly. Or rather, we were trying to do everything by hand, and in a specific case. Okay, so how do we see that this is a semi-algebra? Well, this is actually a lot like your homework problem that is currently assigned. So right now, if you want to show that this is closed under intersections and has the semi-algebra weird complement property, this would split into so many cases and it would be a massive pain. But it can be shown in a similar way to what you see me do on your homework. It can be shown that these things that we're collecting here, which look like four different types of things, can be described as this one type of thing with just the one sort of unifying property, which is that they're the subsets of the unit interval with the property that whenever two points are in there, whenever they contain two certain points, they must then contain all the points in between as well. That's sort of what it means to be an interval. So if you go with this unified description, then it becomes really not so difficult to prove that this is a semi-algebra of sets on the unit interval. And I will not do it here because it's very similar to what you're doing on your homework. Basically, your homework is just a version of this that looks at only the rational points, basically looking only at rational intervals rather than real intervals. But the arguments for why this is a semi-algebra will be the same almost as the arguments that you're making. So, so much for A naught. What about A, the collection of elementary subsets of the unit interval? That's the collection of finite unions of things in A naught. And now, looking back at this, we actually also have good terminology to describe what this is. This is the algebra of sets generated by this semi-algebra of sets. And if you remember from that first lecture about measure theory, when we got here, when we built this algebra of sets, we tried to extend it since it didn't contain, enough sets. It didn't contain as many sets as we wanted. So we tried to grow it, and we grew it into something we called A prime, which was the collection of Jordan measurable sets. And that was strictly bigger, contained a lot more stuff, but still not enough stuff. Sadly, this was not a sigma algebra. So let's stop here with this example for now, and then pick up later. Maybe later we can create a sigma algebra. For now, I'm actually not so much concerned with stepping over to sigma algebra, since we have not developed the general theory for that. We have not developed enough general theory for that yet. But I'm more concerned with the property of countable additivity. So that's what we just got a new toy to play with for the property of countable additivity. So we have this criterion for getting that. So we started by defining some function lambda on this semi-algebra, right? And it was definitely non-negative. And it was given by so we wrote down a bunch of formulas like this, but you have to write down like 4 different formulas for the 4 different types of intervals that can be in there. I think I personally like writing things like this better. And then just say that this is when S is not empty. That's when the sup and inf exist. And then when S is empty, then we define it to be 0. So that just quickly says that it's going to send all of the things of these individual forms you see here to just B minus A. Now, lambda is an additive function on this semi-algebra. This is also similar to something on your homework. Your homework just has a rational intervals version of this. And I ask you to think about additivity. It's going to be a similar situation to what's here, but I don't ask you to write anything because it's kind of actually annoying, and on that homework it's besides the point to write it out. Or at least it's a little bit tangential to the actual point that homework is trying to make. But let's just think about what would go into proving that lambda is additive. So finite additivity, that's what the additive means, finitely additive. Finite additivity refers to those situations where you have a finite collection of sets, like S1 through Sn, in your semi-algebra, such that also their disjoint, pairwise disjoint, and such that also their union is also in the semi-algebra. So that's not an automatic thing, right? When the sets are in the semi-algebra, the union might not be. So a union of intervals is not necessarily going to be in A0, right? It's not necessarily going to be another interval. But additivity for a function on a semi-algebra is only going to worry about situations where you're talking about a bunch of intervals whose union is also an interval. So you have to think about what it takes for that to happen. When will it be that a bunch of intervals have their union being an interval? Well, they have to line up end to end, basically. So something like this, for example, they have to be, or no, not like this, because this excludes 1/3 in a way that will make it not an interval. It will fail to satisfy this property. But something like this, maybe. So they have to line up end to end. They have to sort of connect together so that you don't end up with holes, so that it retains this interval property. Or another way to put it is it can be written as an actual interval. And then you'd have to show that in all situations like this, when you apply lambda to the union, which by definition that would give you this number minus that number, then that's the same as the sum of the lambdas. So lambda of this plus lambda of that plus lambda of that plus lambda of that. And that ends up working because of the sort of telescoping sum, right? You get a negative 1/3, or sorry, you get a 1/3 here and then a minus 1/3 here, and so on. So intermediate terms cancel, and you get that lambda of this thing equals the sum of the lambdas. But what does take a lot of work, I think, is rigorously proving that I think it's a bit of effort to rigorously prove that if you have a family of disjoint intervals whose union is an interval, then they must be something you can write sort of in this format where they line up end to end like this. But hopefully that's plausible, that can be worked out. So lambda is an additive function on this semi-algebra A0. Okay, so we have an additive function on a semi-algebra. Then we know that when you have an additive function lambda on a semi-algebra A0, that there will be a unique additive extension to the algebra of sets generated by the semi-algebra. So that was proposition, let me look that up. It was proposition 1.3.10. And so this is something we did kind of say this in that first introductory lecture about measure theory when we introduced lambda. We did try to, like, quote, define lambda on A, on the collection of elementary sets, by saying, oh, it just extends this formula on intervals in an additive way. We did try to do that, but there was a well-definedness problem when we did that, and we sort of just skipped over it. We glossed over it. So that was really not a complete story back then. That well-definedness problem gets resolved in proposition 1.3.10, and it's worked out that, okay, if you're really starting with a semi-algebra and an additive function, then you do get a well-defined additive extension to the algebra of sets that it generates. Okay, so I'm just pointing out that theory helps us do that step properly now. And finally, is lambda, so what should I call the extension? I called let me just also call it lambda. So as lambda is the extended version of lambda, this version that's defined on elementary sets, is it countably additive? And we now have a tool for showing something like that. Instead of having to fiddle with infinite series or continuity from below or whatever, we can try to use this criterion. So we do have a additive function on an algebra of sets. For us, the algebra is this. And so one way to prove that it's countably additive is to show that there is a compact class of sets, K, which is an approximating class for that function. So here goes. We can use for K, we can use the collection of finite unions of closed intervals. So if you take a finite union of compact sets, you get a compact set. And so when you do this, so by closed intervals here, by the way, I mean closed intervals inside the unit interval, which is the sort of universe that we're working in. So when you take finite unions of closed intervals, those are finite unions of compact sets, so they're compact sets. So K would be a collection of compact sets. And we discussed that this is one of the prime examples of what makes a compact class. And we looked in our old textbook Abbott at how that's actually just a way of stating the nested compact set property. So this is definitely a compact class. What else do we need? It's a compact class. Is it also an approximating class for mu? Not mu, but for lambda here. So okay, so it's a collection of compact sets, so it is a compact class. Don't let that mislead you. This is a theorem, not the definition of compact class. Remember, the definition of compact class has nothing to do with topological compactness. And then question is this collection of sets, fancy K, is it an approximating class for lambda? So let's see. This is now like the what I need to show basically is that condition that I labeled flower in the previous lecture holds for K and lambda. And by the way, we are actually in the simpler situation, which is the situation we're usually in, where K is actually a subset of the algebra of sets. Right? Like finite unions of closed intervals are examples of finite unions of intervals, right? This is the collection of finite unions of all intervals. This is finite unions of closed intervals. So to verify that this is an approximating class for lambda, we don't need the full definition of approximating class, the thing I labeled flower. We can use the simpler version, which is the thing I labeled leaf last time, which I'm going to remind you what that is. Let A be in there, then we just need to show that for any A in there, that, not mu, but lambda, A, is the supremum of the lambda k's running over K in fancy K. So what I mean here is that this is what we need. So do we have this? So let's actually let epsilon be greater than 0, and let's write A as a finite union of intervals. So suppose, I mean, that's what it means to say A is in there. It's that A is a finite union of intervals. So suppose A is, let's say, S1 union Sn, where S1 through Sn are in there. And we can take them to be disjoint, right? And you can just think about why, but also it comes from general theory that we could take them to be disjoint. That was lemma 1214. Tells us that when you generate an algebra from a semi-algebra, you can just take disjoint unions, and that's sufficient. Now let's, I guess you could have the empty set showing up there. That's technically disjoint from everything. So, I mean, it's not going to hurt anything if the empty set is there. Let's just remove it if it's there. So we may assume, how about I'll just assume it's not, how about I just write the word non-empty here, disjoint, non-empty. So if the empty set showed up in this list, just kick it out. You still have this union, you still have this equality. So the reason I care about that is I want to define an to be the infimum, or ai to be the infimum of si, and bi to be the supremum of si. So I don't have to keep writing supremum infimum. Do that for each I from 1 through n. And now let's see. So if I build something, a closed interval like this, ai plus a little bit, comma, bi minus a little bit, then, well, let's see. So let me just pick some size, let's call it epsilon naught, and then I'll decide what epsilon naught should be. So let's just do this. Let's build a closed interval that sort of lives inside s sub I, and do that for each I. Do that for each I. Let's take the union of this from I equals 1 to n, and let's let k be that. So let k equal this. So then k is a finite union of closed intervals inside of the unit interval. So k is in our compact class. And maybe to make the notation easier, I'll just call this k sub I. So let's just call this k sub I. Then can you see what's going to happen when I look at the difference lambda a minus lambda k? So lambda a is going to be the sum of these, bi minus ai, and then lambda k is going to be the sum of these here. Oh, I just realized that I wrote some nonsense up here. This is not the supremum over all k in the compact class. It's the supremum over the k in the compact class that are inside of A here, right? That's what it was. That was the condition called leaf last time that we needed, that we need now. So it's important to note not only that k is in the compact class, but also that k is a subset of the A that we started with here. That's because each ki is a subset of the corresponding si. And the way you would verify that ki is a subset of si would be to use the fact that the si's are in A naught, meaning they are intervals. And then what I would suggest is to use this notion of interval, that whenever they contain two things, they contain everything in between. So that's how we can be sure that each of these ki's is inside the corresponding si. Okay, back to this calculation. So what happens when you do this? Bunch of algebra, bunch of cancellation, and I think we get 2n epsilon naught out of here. So the bi's and the ai's all cancel, right? And then there's n terms, and they're just two epsilon naughts and added n times. Yeah, so you get this. And hopefully there's a vivid picture in your head. There's a vivid picture here, right? Epsilon naught is like, so the SIs are like these intervals, right? And then what we're doing is taking some closed intervals inside, and the distance here is epsilon naught, right? And then we're getting, there's two of these little blue segments, each of length epsilon naught, so 2 times epsilon naught is the total length for one of these n total intervals that we have. So, yeah, so we can make epsilon naught as small of a positive number as we want, and this will all still work, right? So let's see, did I fix an epsilon? Yeah, I fixed an epsilon greater than 0 up here. So how about I go ahead at this stage and instead of putting epsilon naught, choose epsilon over 2n. Okay, so I've got epsilon at the end here. So since epsilon can be made arbitrarily small, that tells you that there are lambda k's that are arbitrarily close to lambda a. And of course lambda a is an upper bound for the lambda k's. So lambda a is the supremum of the lambda k's. So then yes, this is an approximating class for lambda. So what did we achieve? We have a compact class, fancy K, which is an approximating class for lambda, which is our known additive function on the algebra of elementary sets inside the unit interval. Conclusion, thanks to theorem 143 from last time, conclusion, lambda is countably additive by theorem 143. Which is pretty exciting. So I find it really interesting to compare this whole situation here with what's going on in your currently assigned homework problem. So let me scroll back up here. On your homework, you've got this being a collection of sort of like elementary, oh sorry, no, you don't have this. You have like more like A naught, right? You've got the semi-algebra of intervals, but they're rational intervals. So instead of just this condition, you also require that that they contain only rational points in the unit interval. And yeah, so you never go to an algebra of sets. You stick with the semi-algebra level. But you show that, or you think about why lambda would be additive, but you show that lambda is not countably additive, right? So, well, you could, in your rational interval setting, you could look at the algebra of sets generated by that semi-algebra. Since your lambda is additive on the semi-algebra, it extends uniquely to an additive function on the algebra of sets. But since you show on your homework that your lambda is not countably additive on the semi-algebra, it must not be countably additive on the algebra, right? Since whatever counterexample for countable additivity you found in the semi-algebra can be used in the algebra of sets, which contains the semi-algebra as a subset. So you have a non-countably additive thing, but it still has this definition, basically, right? It's just that you're only allowing rational points in your intervals. But it's still, your lambda still has this definition. So what gives? Well, I mean, you find a counterexample, but what I find interesting is just to think about why the approach here doesn't work for proving countable additivity in that rational setting on your homework. So why can't we just let K be the collection of finite unions of closed rational intervals inside there? And if you're worried about whether the endpoints are rational or not, you can make them rational or not. Regardless, I think the argument here that k is an approximating class for lambda would still work. I don't see anything that would fail here. I mean, sure, epsilon over, epsilon might not be a rational number or something, but you can use only rational numbers here, right? Like, it would still work. So I think you would still have k being an approximating class. But somehow something's wrong, because you don't end up with something countably additive. So can you figure out what goes wrong there?